Okay, so good morning everyone. Say morning, just morning, just gone over the 12 o'clock. So we've now finished two big chunks of the work that we need to do, and we're now going to start looking at power supplies and regulators. Excuse me, still coughing. So there'll be a bit of a recap of what regulators are, and then we'll go into a bit more detail about how they work and things like that, and then we'll round this off with looking at some switch capacitance circuits, which is emulating resistors using capacitances and switching them really fast, which is quite a neat way of doing things, and then that has quite a lot of application in A to D converters and stuff, which comes later. So in many ways we're seeing the same techniques being used over and over again, which is good. So I looked at the schedule. We're a little bit behind, but I don't think it's going to cause us a problem, depending on what happens after Easter though. So there's some thought that we might go back to face-to-face, which will need a bit of planning, I think. Anyway, let's crack on with this. Let's get rid of that. Okay, so regulators, as discussed. So this is all to do with conversion of power and allowing circuits to have the power supplies that they need to operate. So it's conversion of power, really. So in any circuit we're going to require power. Power is one of the biggest problems of people when they're designing circuits. They don't think about it very much at all, really. So we need to consider where our power can come from, and it can come from many sources that we're aware of. Batteries. Okay, so batteries is a general case, but different batteries have different characteristics, different output voltages, different current delivering capabilities. Some are rechargeable, such as nickel cadmium or lithium ion, and various other flavours these days, and some are called primary batteries, which are not rechargeable, such as alkaline batteries or silver oxide coin cells that go into watches and things like that. Other sources of power will obviously be the mains power, but that depends where you are in the world as to what that is. So in the UK it's 240 volts at 50 hertz, and the 50 hertz is very well controlled, and 240 volts is reasonably well controlled. In other parts of the world we might get 110 volts at 60 hertz, and in certain parts of the world this 60 hertz is a sort of an ambition rather than a specification. Likewise the amplitude, so there's quite a lot of variability potentially in power coming through. And then we might find that we're getting power from other sources, and some of the things that I'd be interested in would be energy harvesting from the environment, solar cells for example, even local generation. So in the old days bikes used to have dynamos attached to them that would light the lights up, so the more you pedalled the more light you got. Obviously you could charge a battery and make it a bit more sensible, and this sort of thing I'm sure is going to coming back, and sort of regenerative braking in cars is another version of this. So there's lots of different sources of power is what I'm trying to say, really. And most electronic circuits operate best, particularly precision circuits, when the power to them, or at least the voltage to them, is controlled. This would be the normal way of doing things. Most electronic systems require a fixed voltage to work at, and that might be 3.3 volts, might be 3 volts, might be 5 volts, might be lower these days. And that voltage should not change as load conditions are changed. So we want 3.3 volts out of here, irrespective of what current is being drawn here. So we want this to be an ideal voltage source, or as close as possible to that, which is, a good ask. An ideal voltage source is ideal, and it's going to be hard to make one. But not only that, we've got a varying input to this converter as well. So this input here needs to not affect the output over here as much as possible. So this is asking quite a lot out of this box to maintain this voltage at 3.3 volts, irrespective of the load taking current out and irrespective of the input that's coming in. So that's sort of what we're trying to achieve in the main thrust of power supplies anyway. So, as it says, unsurprisingly, a single circuit does not exist to cover all the possible input scenarios. So, if we design a power subsystem, we may have several steps or blocks, and we should be getting the idea of the idea of system diagrams, where we can break our overall problem into little chunks, and then we can define those chunks and then work out what goes in these boxes to achieve the input and output specifications of each block. And those will plug together, hopefully, to make the overall converter with its general spec on the output. And some of these blocks may well even be divided into sub-blocks as well, which we can then start to implement architectures in there. So this is a common situation. The input is AC, 240 volts AC main supply, and we want to turn it into 3.3 volts. So we need to understand how we might get there. So one common architecture for that is to take the 240 volts down to a value which electronics can deal with more easily. So we have an AC to AC conversion down to 18 volts or so typically, and then we'd have an AC to DC conversion. So this takes our AC and squashes it down into a sort of a DC, but it's maybe not well controlled, might be a bit lumpy, but it's still DC of a form. And then we have a final DC to DC conversion, which takes this reasonably well controlled input, converts it down to 3.3 volts, which is really well controlled. And this bit is the bit that we're going to be concentrating on in here, because this is a transformer and this is a rectifier, and this is the clever bit. So there are two main classes of regulator that can go in that box, linear and switching, and we're going to look at both kinds of those. You will have done a bit of linear work last year, but it's worth recapping that just to get an idea of where the advantages and the limits lie within that kind of system. So the requirements of an output voltage should not change for changes in current demand, so that's changes in the output, implies an ideal voltage source, as we've just discussed. And an ideal voltage source, an ideal one, has an effective output resistance which is 0. It says very low, but if it's truly ideal, then it is 0. We can't get that. But a good way of achieving this is to provide feedback within this block. So what we're effectively doing is saying that if this load changes, and in this non-ideal world, this means that this voltage will drop or at least change depending on which way this current goes. We can compensate for that by increasing this voltage accordingly. So this voltage is going up and down to maintain this voltage at the same point as the load, the current, varies through this system, and that implies feedback. And this is what we're effectively saying down here. So it's a long-winded way of saying the same thing. And then what we're trying to say in here is that although this doesn't actually change or make the output impedance of this 0, what it's really doing is making the dynamic output impedance of this system equal or close to 0. And the dynamic output impedance is given by rate of change of voltage with current. So if we can keep the change of voltage at this point low, irrespective of what the current does, then effectively we've said that the dynamic impedance is really, really low, and that's what we're doing here by changing this voltage up and down. It's just maintaining this voltage at a given point irrespective of the current, and that translates to a dynamic impedance that's really low, even if this real impedance isn't low. And that's really what we're just trying to say, really. It's a subtle point, and it's not that important in the great scheme of things, but that's how we can get an effective 0 impedance when the real impedance that you would look at measuring this is not 0. But to actually drop the voltage in the first place, the series regulator looks a bit like a variable resistor. So we're saying we want a certain voltage out of here, and we've got a certain voltage coming in. We're going to have to lose some voltage, even if we're going to then maintain this voltage at a fixed point. So we can view it as a variable resistor. It's not strictly speaking obviously a variable resistor, but that's this kind of idea, and it allows us to then see where the drawbacks of this type of system might lie. V out or V has to be larger than V out. This voltage here needs to be higher than this volt because we need to lose some voltage to maintain this one here. And V out, this point here, is then altered by measuring it and then comparing it to a fixed reference somewhere in here and then adjusting this voltage accordingly. The problem with this approach is that it's quite wasteful, because under a set of conditions where we're dropping voltage across this equivalent resistance to supply the load at a fixed voltage here, then this current is still flowing through a resistance, so we're going to be dissipating power in this part of the system. Okay, so and what you can actually feel this in a linear regulator. If you put your fingers on it, you'll probably burn yourself because they do get really, really hot really quickly. To give you some idea of what's going on, if we had a 5-volt regulator, so we've got 5 volts coming out of here and we've got a 10-volt supply coming into it, and the load is asking for 1 amp, then we want 5 volts here, we've got 10 volts here, we've got to lose 5 volts across this part of the system before we can give 5 volts to the system here. There's still 1 amp going, and whichever way you cut it, if you're losing 5 volts through a resistor at 1 amp, you're going to be you're going to be dissipating 5 watts of power, which is quite a lot. So as this voltage goes higher and higher, as you know, then the amount of dissipation in this part becomes higher and higher as well. And you will see going forward that linear voltage regulators tend to have big heat sinks on them, and they're in big chunky packets, and data sheets will tell you that you need to make sure that they're connected to a big lump so that any heat can be dissipated, because we've got a lecture later on that talks about heat and power, and in fact the biggest killer of electronic circuits is heat. If they overheat too much, they will damage themselves and be broken. And so heat is a big issue, and this is an obvious source of heat. It's also very inefficient, and in the modern world we like to be efficient if we can. So linear regulators don't tend to be terribly efficient. They're not bad if you can drop this voltage right down to be close. So if you wanted a 5-volt regulator, if you could actually make sure that this was close to 5, so between 5 and 6, then actually they're not too bad. But it's quite difficult to design linear regulators that have this headroom, a very small amount of headroom there. But anyway, they're very low noise, which is nice. So you get a very smooth power supply here, at the consequence of a little bit of waste. So a simple regulator, how we might build one of these things, we can do it with effectively a single transistor, and with a little bit of feedback that's being applied in here. And the way these sort of things work is you need a fixed voltage reference to compare against, irrespective of whether this voltage is going up or down or not. And in this simple case, this is achieved by a reverse biased Zener diode. And so we can tell from this name here with the 6V2 that it's a 6.2 volt Zener diode, which means it will break down in the reverse direction at 6.2 volts and conduct backwards through itself. So at 6.2 volts here, this will start to conduct in this direction here, and it will conduct as much current as necessary to maintain this voltage at the Zener voltage, which is 6.2 volts. So whatever the voltage is here doesn't really matter. The current through here will adjust itself to maintain 6.2 volts at this point here. So we've got a fixed voltage, as fixed as a Zener is anyway, which is it's not great because it's a junction diode, but it's a good approximation. Right. So what we've got is an amount of current flowing through here, and some going into the transistor as well to make the transistor on, to keep it going. And what we're trying to do is maintain the voltage here, which gives us a fixed VBE across here when this is conducting, and that will give us a form of regulation. So when the transistor's on, we've always got 0.7 volt across here. We've always got 6.2 volts across here when this is operating. So what we're going to get is 6.2 minus whatever VBE is across here, which is if we assume transistors on, we can call it about 0.7. So we will always get 5.5 volts in this particular system out as our target voltage, assuming everything is on and flowing happily. And if you analyze this within LT-Spice and see what's going on, you can see that as the input voltage starts to rise, the output voltage is following, but will be a bit behind because there's some losses across the transistor, and the transistor isn't on properly yet because there isn't enough voltage in the system to turn everything on properly. And at about 6.2 volts or so, as this voltage starts to rise above 6.2 volts, then this Zener is allowed to start to conduct and maintain this voltage at 6.2 volts, and that will then maintain the output voltage at 6.2 volts minus the VBE drop in this transistor, which you can see start to flat. So even though the input voltage is then rising significantly, we're starting to get regulation at above 6.2 volts of input, and it's relatively flat. Okay, so quite a simple system. Got a varying voltage there, we've got a fixed voltage here, and we're assuming that when the transistor's on, the VBE is fairly constant. Obviously varies a little bit, but not a great deal, so we get a pretty good amount of variation, pretty good amount of regulation, I should say. Regulation being that the output is not changing very much. Okay, and then there's a bit of a zoom in at the corner there, so you can see how things are starting to operate properly. It's quite instructing if you then take this circuit, put it into something like LT-Spice, and then investigate the various currents and voltages as you sweep these things. So you can take this circuit, put it into LT-Spice, and try it out if you want. Right, so as we increase the load current, so that was giving us an output voltage, and we've got a fixed load at this point here, so we're going to end nothing much going on. So we've stabilized the output here for changes in the input above 6.2 volts anyway. If we then start to vary this, we would still like this voltage to stay the same, but obviously we want the current to vary. So we can run the same kind of simulation to see what's going on. In this case, we've got a current source as our load rather than a variable resistor, because it's just more convenient to be able to sweep that, and then we can just sweep that current source in here from 0.005 amps up to 0.1 of an amp, so 100 milliamps in steps of 0.005. So and that allows us to run a simulation to see what happens as we vary this current here, and you can see that what happens is that the output voltage with output current maintains its 5.5-ish volts. It's starting to drop a bit, but it's not too bad until you get to a certain point where we're starting then to limit ourselves in the amount of current that we can provide through this system. And that's happening because we keep demanding more and more current through here, and eventually the base current will exceed the current allowed that the Zener wants to keep itself on, and then this starts to fall, and we end up starting to fall off. So under these conditions, for this particular type of transistor, we get about 60 milliamps of current, which isn't great. But if you are operating over when this is not changing very much, then designing for that particular operating condition is not a bad idea in many ways. So in summary, the simple circuit above gives us an output voltage given by Vout equals Vz minus VBE, where this is Vz and this is VBE, and we're assuming that VBE isn't changing very much, but obviously at some point it will change, and it starts to change when either the input voltage is too low or the output current we're pulling through is too high for the base drive to maintain a VBA of 0.7 here. So the problem we have with that is that it's limited to regulating at a fixed voltage, and that's defined by the Zener diode, and there aren't that many Zener diodes to choose from in terms of the voltage, so we're a bit limited in our potential output voltages that we can design a regulator for. So we'd like something that's a little bit more flexible in how it operates. So what we can do is we can sample the output voltage at any point, really, at any level, and use that to match the input to our Zener diode. So we've made a little comparator here in some ways. So we sample it by putting a potential divider on the output, and then we can obviously change the value of this potential divider to give us any fraction of the output voltage we're interested in. And the resistors R2 and R3, these one here, they give us this potential divider, and that will sample a fraction of the output voltage, and that's just a potential divider. So it's whatever V out is over R3 over R2 plus R3, which is just the potential divider equation here. So this voltage here is a fraction of this voltage here, and that fraction, it's easier just to call that K rather than R3 over R2 plus R3. So as Vs rises, which you will do as this voltage rises, VBE of Q2, this bit here, will also start to rise, drawing more current, and as that happens, more current falls through here, it pulls off more current here, drops this one, reduces the amount of current flowing through here, and then Vs will start to drop back again. So that will help us control the final output voltage. So under sort of normal conditions, if you like, the emitter end here is held at the Zener voltage, assuming there's current flowing through here. So that Vz plus the VBE of Q2 is equal to Vs, so that's just adding those two voltages there. Therefore Vz plus VBE must equal to kV out, because kV out is defined as Vs in here. So we can then define V out as being Vz for any Zener that we happen to have chosen, plus VBE, which we're going to be assuming is 0.7 of a volt for any given transistor if it's on, and we want it to be on, divided by K. And K is something that we have control of because it's related to our output voltage and these two extra resistors we've added. So as it says in the diagram above, K equals 0.8 if we took these values and calculated K from V out. And Vz is equal to 6.2 because we've got a 6.2 volt Zener. And if we assume that VB is 0.7 when on, this will give us an output V out as 8.6 volts. If we just put the numbers into there as a working starting point. And sure enough, if you simulate that, you can see that we're above 8.5, below 9, so about 8.6, and again works reasonably well. And then we'll start to fail as we start to draw more and more current out of it, and we run out of base drive. Not completely flat, and that's just down to the gain of the transistor not being huge. If we had something with higher gain, we can make a much better circuit. And one way of doing that is to include an op-amp into the circuit. This allows us to not have a variation in voltage at this point then. Right, so effectively what we're saying is that this voltage here needs to be bigger than the Zener voltage, but then we would always get a fixed voltage at this point here. And because there's no current drawn into the op-amp, there's no loading effects, so this voltage will not go up and down significantly, certainly not with output load anyway. Might go up a little bit with this. That's then, this area amplifier then is then sampling the output voltage here and comparing that with its input, and it's adjusting its output to maintain a difference of 0 at its inputs. So that's a standard op-amp type circuit. So it's the transistor but just made better with a much higher gain. And then you can see then that everything works a bit more smoothly. Okay, and again we can just adjust this ratio here to give us a different voltage that we're going to compare against this point here, and this point here is going to be 6.2 volts in an ideal world. So whatever we need to divide this down to give us 6.2 volts here will give us our final output voltage. And again, if we increase the output current as before, we're going to see that we actually got a lot better regulation now. The voltage stays very close to the design voltage and then drops away very quickly. And look, the numbers down here are much higher. We only had about 60 milliamps with our single transistor, which was struggling a bit. But because our op-amp can drive a lot more base current, we find that we can get a lot more dynamic range of currents out of such a simple system. And it says here we can get up to about 1.4 amps out instead of the 60 milliamps that we got in the previous case with the same transistor in the as the pass transistor. So this is a really sort of useful configuration, and it's available in a single package for ease of use. And you may be familiar with the 7805, which is a very old but very stable and very useful device. Fixed output voltage of 5 volts in this case, but they come in all kinds of different flavors and can provide up to about 1.5 amps of current, so very similar to what we've done with our very simple system. So if you haven't got a 7805, you can build one with any old op amp. This is quite a small transistor for any old transistor, a few resistors, but you do need a Zener or some kind of fixed voltage here. If you can guarantee that this voltage isn't going to move, you can replace this with a potential divider. The only problem is that if this voltage moves, a potential divider's voltage will also move, because that's what we're relying on over here. And the Zener is the thing that gives us our fixed voltage. You could replace the Zener with a normal diode and give you 0.7 of a volt, or even a cascade of diodes if you want to. So there is scope for playing around with this, because then all you've got to do is adjust the potential divider to give you the voltage you want. Okay, so that's actually quite a nice system now. When we've included the op amp with a high gain, with good feedback, works really nicely. I say the only real problem is that they're just wasteful of energy. If you put a big voltage in and get a small voltage out, it has to dissipate quite a lot of energy within itself. Because there's an op amp in there as well, we also know that there's a virtual earth system involved in this because it's negative feedback, and so if there's any kind of high frequency efforts, if you're trying to pull currents out of this into a system that's changing it's turning itself on and off really fast, and it's taking big currents and small currents, that can cause some issues, because the virtual earth in the op amp will start to fail at high frequencies and you won't get the high gain, and then you will get some ripple on the power supply, and that can lead to strange effects. So just got to be aware of that. It's not normally a problem, but it could be, because it's just a feedback system relying on a virtual earth. Okay, so to sort of summarize on linear regulators, important points to be aware of are dropout voltage, which is the minimum input voltage needed to keep it working. So in the case we've been looking at, it's been the voltage of the Zener diode, so 6.2 volts or so. So if your input voltage drops below that, then your regulator will stop regulating. This thing called output voltage regulation, which is how much the output voltage varies with changes of input voltage, and a good one will have a very low number for this. And if you look at the data sheets for the 7805, it's about 5 millivolts of variation of output voltage if the input varies between 10 and 25 volts. So that's pretty good, really. You're guaranteed to get 5 volts plus or minus 5 millivolts for any input voltage between these ranges. But look, it's 10 and the output voltage is 5, so you've still got 5 volts of headroom to worry about. And then ripple rejection, how well variations at the input are suppressed. So if you've got a 50 Hz ripple coming in, we don't want to see a 50 Hz ripple on the output. So there's got to be a certain amount of suppression, ripple rejection going on. So these are numbers that you'll see on the data sheets. But for a linear regulator, they're usually pretty good now. One thing we haven't talked about is overcurrent protection. There can be faults in systems that lead to usually short circuits, although open circuits can be equally a bad problem, particularly in current circuits. So you might want to build in some form of protection. So we're all going to be familiar with fuses. They're quite crude because they break and then you have to replace them. And then, as we discussed in the very first lecture, if you replace fuses with the wrong item, you can lead to personal damage, which we don't want to happen, really. So it'd be nice to have a circuit that could act like an electronic fuse but didn't pop and could be reset. And if we're talking about power circuits, we do really need to talk a little bit about protection, because it's power circuits that tend to supply the whole of the rest of your circuitry. So this is the place where it's going to be easiest to detect any kind of problems. And if you can protect the rest of the circuitry at the power source, then that's obviously a good thing to do. So we've seen in the last one that some of these systems are inherently self-limiting anyway. With a single transistor we only got a maximum of 60 milliamps out of our regulator anyway, but then we saw that when we improved the design, we ended up with a lot more current, orders of magnitude higher potentially, of 1.4 amps or so. And it could be that we can get a lot more out as well with even better designs, and it could be that under certain conditions we don't want to get all that current out because it's indicative of a fault condition somewhere in the circuit, so it's too big a current at the wrong time. So what we can do is put a bit of monitoring into the output of these systems. We can see this is our the transistor, the pass transistor we had in the previous circuit, and now we've added a sensing resistor. So as the current delivered to the load rises, the voltage across this sensing resistor will also rise, and if we use that to control the state of this transistor, we can effectively make a limit switch. So what we're really hoping for is that as the current rises through here and the voltage across here rises, at some point we just want to trigger this transistor and say this transistor's on, and that will then pull all the drive current away from this transistor and effectively reduce the current flowing through this one, turn it off in certain cases. So all we need to say is, if we just put this in the way, and we make sure this is a small resistor as well, what we want to know is when does this transistor turn on, and we would say, for the sake of argument, turns on 0.7 of a volt across it. So what we're really saying is, at what current does this voltage across here become 0.7 of a volt, and that will be the time that this circuit is triggered and we start to pull the drive current away from this transistor. So that's simple enough. We're just applying Ohm's law across here, and if we do that, we can say that the maximum we're interested in voltage for turning this transistor on is, say, 0.7 of a volt, and that's going to be equivalent to the maximum design current through here multiplied by the value of the resistance. And then to rearrange that, you get I max is VBE max, which we're saying is arbitrarily 0.7 of a volt, over the value of the resistance. So if we know this, if this is what we're designing for, and we know this already, we can work out what R is. And that becomes quite a simple little technique. So if we just added that to our simple regulator, it allows us to include this overcurrent protection in the output here, and that's there's not much more to say about it. We just drop this bit in to our simple regulator, so now we should be able to control the output current and get it to turn off, or at least drop the current at a known point. And then if you do that with R4 set to 10 ohms, it gives a maximum current of 70 milliamps in this design. So I've changed some of the values from the previous example just because that actually cut off at 61 milliamps. So with R4 set to 10 ohms, then obviously we've got when we're looking for 0.7 of a volt across it, that gives us 70 milliamps going through. And if we simulate this, you can see it drops off a little bit before 70, but not too far off. But that's because we chose VBE as 0.7, and actually if you investigated that transistor in a bit more detail, you'd see it as 0.65. But that's where detailed design comes in and the use of the simulator. You put in what you want, take your initial estimates, get it into the right sort of area, and then you have to go and tweak things to find out what's causing the variations. So the drawback about this type of protection is that short circuit current here is the maximum current. It's 71 milliamps, so you've got a short circuit, you've still got 71 milliamps flowing on your circuit, and if you've got a short circuit condition, you might not want to have this maximum current being pulled through. You might say, let's identify the short circuit condition and then reduce the maximum current that can flow. And this is done with a neat little circuit called a fold-back circuit. And we're looking for this type of output configuration. So we get our maximum current out, or maximum voltage out for up to a given current, and then when we exceed that, instead of it dropping down here and giving us a maximum current at in the short circuit conditions, what actually happens is it folds back on itself, and so we actually end up at this point here where we've reduced the maximum current that can fly under those conditions. So we've made a sort of unstable little circuit really. So it doesn't really follow this trace in any kind of sensible way, because under a fault condition what happens, it pings along here, zips out and pings down, and then gets to this point here. So you won't see it in this state, but this is effectively what the maths ends up doing. So what we're really saying is that we've got under normal conditions we can operate up to this point here in terms of current load. So we can vary our load, get our fixed voltage out up to that maximum current there, but if we go above that, it'll flick to this state here where it's a short circuit condition, and the maximum current will then drop. Okay, so that's what we're trying to achieve. We're trying to just really gently fold back the current on itself, and so we can do that relatively straightforward by adding in a little bit more complexity into the circuit. Excuse me. So Q1 is what we're looking to protect. This is our pass transistor that's providing all the current. We've got our reference comparison going on here. We've got effectively our protecting transistor happening here, but we've introduced now this sort of potential divider into the circuit as well. So once the sensed current is detected as being too high through here, Q3 turns on, which is what we expected, which reduces the base current seen by Q1, so that's starting to pull more current away from this system here. The transistor then starts to reduce the current it allows to flow, so this current is now starting to reduce, and if the load is still demanding more current because it's a short circuit, for example, then this process continues furthermore, and Q3 will turn on more and more as more and more current is pulled through here, and thus as more and more current is tried to pull through here, this turns on more and more, and this one is turned off more and more, but it all doesn't happen instantly, and so the maximum current that's allowed to fall is reduced. And to get to see how this happens, we can look at the voltage at the emitter of Q1, which is VA, and that's given by I0 R4, which is the output current, divided by multiplied rather by the value of that resistance there, plus whatever Vout actually is. So it's just the current going through there, so it's the voltage drop across that resistor. Thus the voltage at the base of Q3, neglecting any base current, so we've said it's been biased with a significant current down here, is going to be the potential divider made up of R5 and R6, and then multiplied by whatever voltage we're getting, the potential divider multiplied by the scale factor, which is VA, that's the voltage across it, and that gives us the voltage of VB. So VB is this potential divider here, and we know what VA is because we've calculated it from here. So again, justifying a new K primed as being this voltage divider ratio gives us the base voltage is equal to K primed, which is the ratio of two resistances, multiplied by some function of the output. So you can then go round the mesh at the base of Q3 and work out that Vout plus VBE, so Vout and that bit there, is equal to V base. So we're going from here, we're going through VBE, and that gets us to VB. So VBE is equal to VB minus Vout. Just rearrange this, and we know that VB is this, so that allows us to rearrange this, and we end up then with this expression here with K dashes appearing twice, a Vout and an I0 that we're interested in. So that leads us to this equation here, where the maximum current that can flow occurs when the VBE is max, i.e. this transistor is about to turn on but just hasn't quite turned on. We're assuming that it's either on or off, which is maybe not a bit of a false assumption, but it's good enough. And then plus this relationship with K dashed and V out. So that allows us a sort of a set of design conditions to design for the maximum current that we want through this thing, and how we go from there. So under short circuit conditions, V out is 0. So if V out is 0, this expression becomes 0, and this reduces to this. So the short circuit current is defined by VBE max over K dash plus R4. Okay, and then we can just resubstitute in for K dashed, and that allows us with a set of resistances to work out what design for a particular short circuit current. So we've got a way now of designing for a maximum current through our system, and we've got a way of designing for a short circuit current that is now defined as well. So we assume nothing unusual happens until VB is exceeded, so everything behaves normally, so we're assuming nothing's happening at that point. But the interesting thing is what happens when VBE reaches its maximum, and then we're saying actually we end up in this part of the characteristic, which is a straight line, and then the only interesting part of that then becomes this value of the short circuit current. If you remove the short circuit, it goes back to being operating in a normal condition. But what we normally say is that a ratio of I max to I short circuit of not less than a third is usually recommended. If you make this too steep coming back down here, you can actually have trouble turning certain circuits on, because when circuits turn on, particularly inductive circuits, there tends to be an inrush of current, and if your inrush of current exceeds this point here, then the thing assumes a short circuit and switches straight away. So we have to make sure that you give it a bit of headroom for startup conditions. You don't want your fold-back circuit stopping your circuit from actually turning on under normal conditions. So that's just something to watch. Okay, so as a quick example of this design, normally you know what your target value of V out would be. You've got a design value in mind for the maximum current your circuit's going to demand, and you're free to put this where you like, at maybe about a third of what I max would be for protection. So it says first calculate the required values of K primed. This can be done by taking the ratio of I max to IC. So if you took the equations of the previous slide for I max and for IC and ratioed them, lots of things cancel out. You end up with this equation here. We now know that VBE max is going to be 0.7, so that can fit in there quite nicely. Put the 0.7s in, and everything simples down to quite a simple arrangement then. And by simple manipulation of these equations, we end up with a value of K primed, which is dictated by our design parameters, which we've got full control over, so there's no longer any variables in there, and everything is fixed. This gives you a value of K dashed from your design parameters, and then you can just work out what K dashed is by fixing R5, for example, and calculating R6. So K dashed is defined as being R6 over R5 plus 5/6. So all you've got to do is pick a value for one of these two, and then work out, knowing what K dashed is, work out what the other values is. So I've done it long-winded way here, but I'm sure you can think of simple ways of doing that. And then you can use ISC equals VBE max over K dashed R4 to get R4, because we know what K dashed is now, we know what VBE max is, we know what ISC is, and it only leaves R4. So it becomes relatively straightforward once you've understood the design equations for it. So if we have a simple regulator to provide 12 volts with a maximum current value of 1 amp, and we've got a simple current limiter, what is the value of the current limiting resistor that we would need to under these conditions? Okay, well, we need 0.7 of a volts across our transistor, and we know that we want 0.7 of a volt when we've got 1 amp flowing through it, so that simple boils down to 0.7 of an ohm, which is nice. It's a small value, which means there isn't going to be much dissipation through it, so it's not going to get hot and it's not that wasteful. If we now add foldback circuitry to reduce the short circuit current to half an amp, we can go back through the we now got our design variables of maximum current, the short circuit current and the voltage that we're interested in. So we can just go back to the previous slide, look at the definitions and say we need to work out what K dashed is. We put the design variables in, gives us a value of 0.941, and then we can work back to get a value for R4. And once we've got a value of 0.941 for K dash, we can work out the values of the two resistances R5 and R6. And at that point we can then start to put these components in. I haven't actually put the right components in to demonstrate this. These are just examples of the circuits to show you the difference between the two. So this is one that's got current limiting but no foldback, and this one's got the same kind of thing but with foldback added in, just to remind you what's going on. But there's nothing stopping you designing your own limited circuits by using these circuits as examples and trying the whole thing out. So that's a good point to stop, and we move on to switching regulators next week, and they're a bit more interesting, and they're really efficient, so they're good. We'll look at those Monday probably. Okay, so I hope that wasn't too tedious for you. I think that's quite interesting when you start digging into how these transistor circuits actually operate, but there's no replacement for putting them into a simulator and just actually seeing what's going on, because there's some subtlety going on in these things. The principle's okay, but the subtlety can be a bit tricky to get sometimes. Okay, so I'll stop there. See you next week.